Baby girls, welcome back. Today we are going to talk about what's known as the law of conservation of momentum. So last section we looked at the idea of momentum as a measurement, again, of how much motion an object has. So it's the object's mass times the speed. And we also focused on the idea of what's called impulse, where an object's momentum could potentially change. And that impulse is caused by a force acting over a given amount of time. Connecting these values, we said that an impulse causes a change in momentum. So we had that force acting over a certain amount of time causes an object to move. This is called the impulse momentum change theorem. So what we're going to look at today is what's called the law of conservation of momentum, which is kind of applying this impulse momentum change theorem to a collision between two objects. So the law of conservation of momentum looks at what happens when two objects interact. So the impulse idea simply applies to a single object, but the law of conservation of momentum is going to apply to a system of objects. So what it says is that if one object loses momentum, that momentum essentially has to go somewhere, and that momentum is going to go into whatever took the momentum away from object one. So if you have two objects colliding, for example, if one object loses momentum, the other object is going to gain that same amount so that the total amount of momentum within that system is going to stay conserved. So the idea of conserved means that whatever momentum we have before, I'll label that as PI as initial, should equal the amount of momentum we have afterwards. So for example, you might have seen this apparatus being used before. This is called a Newton's cradle, where this object is dropped so that it's going to gain momentum. It's going to fall down, and as it falls, it's going to gain speed and gain momentum until it collides with these other four objects. Now, essentially what's going to happen when this object collides with these, it's going to lose its momentum, but at the same time, what you're going to see is this object at the end is going to swing back outward. So essentially what happens is that the momentum lost by this first object when it collides is going to be given all the way through, is going to pass all the way through to this last object, and this object's going to start off with no momentum, is going to gain some momentum. So essentially, whatever the momentum is lost by this object is going to be gained by this. So I'll demonstrate this Newton's cradle to you in class so you can kind of see how the law of conservation of momentum works. But this law, again, applies to a lot of different things, almost everything that we see collide. So all this is essentially is an application of Newton's law. So what we learned about is, first of all, Newton's third law, which was the whole idea of action and reaction pairs. So for example, if I have two colliding objects, we talked about that the force of one object on the other is equal to the force of that second object back on the first, okay? So I'll just label this as F1 and F2, that the force of one is going to equal the force of the other. So let me extend on this a little bit further and use Newton's second law. Newton's second law states that when an object experiences force, it's going to accelerate. So an acceleration is going to be equal to that force over the mass. So when these two objects collide, they are both going to experience an acceleration. So I can just kind of rework this equation and say that the force is going to be equal to the mass times that acceleration. So essentially, each object is going to accelerate. So I can use this to kind of rewrite this equation. So substituting in Newton's second law, I could just write M1A1 and M2A2. That's essentially just saying the forces are equal, but we're looking now at the respective masses and the acceleration. Now, we should also know by definition that the acceleration of an object is simply the change in speed over a certain amount of time, meters per second. So it's how much speed the object is gaining or losing. So reworking this, I can take this idea and plug this into the equation so we'll see something familiar. So what I would get is this. Okay, so instead of the acceleration, I'm plugging in the definition of acceleration. Now, what we talked about with that impulse momentum change theorem is that when the objects collide, essentially this collision is going to take the same amount of time. So the only thing equal in these two equations are the time intervals. And essentially, since they're both in the denominator on either side, those are going to cancel out. And what I'm left with is this relationship here that states that the first mass times its change in speed will equal the second mass times its change in speed. Okay? Now, this, obviously, by definition, mass and speed is the momentum of object one. And this is the momentum of object 2. And specifically when two things collide, we're going to see those momentums change. So this is the idea of the law of conservation of momentum using Newton's second law, that when one object gains momentum, the other object is going to lose. Same thing here, what they're going to gain or lose is going to be all dictated on speed. So one of these delta V's is going to be a loss and the other one is going to be a gain. But essentially, whatever we see, loss or gain is going to be equal on either object. So now we can take this idea and kind of apply it to problems. So here's a problem that has nothing to do with momentum, but it's kind of the idea of loss and gain and things being conserved. So it says here that Jack possesses $100 and Jill possesses $100. Jack pays Jill $50 for his portion of the month's cell phone bill. So what we're going to do is we're going to use this little two-way table. So the two-way table is just a nice, easy way to help understand this idea of change as well as the conservation momentum. So we'll say that object 1 here is Jack and object 2 is Jill. So before the exchange, each person has $100. So if I think of this as a total combined, they're going to have $200. Jack is going to pay Jill. So after Jack pays Jill, Jack is going to have $50, but he gives that $50 to Jill, so that Jill, after the exchange, is going to have $150. But the idea is this, is that even though each of their individual monies is going to change, that in total, it's still going to remain the same. So first of all, by looking at the total, you're going to see that the amount beforehand, this $200, is going to equal the amount that we have afterwards, $200. But when we look at the change, and think of the change as the final, I'll write F minus the initial. So if I take Jack goes from 100 down to 50. So Jack lost $50, where Jill went from 100 up to 150, so Jill gained $50. So the overall change, if you were to take negative 50 plus 50 here, what you're going to see is that the overall change is 0. And this is another way of explaining the conservation of momentum, is that overall the change in momentum is not going to be different. It's going to stay 200, such that if I were to subtract 200 and 200, I'm going to get 0. So this is an idea of money, but it's the same idea we're going to see with momentum. So here's an example of a collision. So I have a cart with a brick. You'll see here that I have some moving cart with a brick, and then there's a brick on top. What's essentially going to happen is as this cart moves underneath, the brick is going to drop down, and the three things are going to move together. So essentially what's going to happen here is the mass of this object is going to get bigger. So if the mass gets bigger, like we talked about in our first section, we should see that the speed is going to get smaller. Okay? So overall, the cart in the initial brick we're going to see is going to lose, but this brick that was not moving initially is going to increase. So again, we can use this two-way table to kind of analyze this situation. So it says here that the cart and brick are going to contain 45 units of momentum before. The brick that's not moving, that's MB up here, this is going to have no momentum. So overall, there's going to be a total of 45 units of momentum in the entire system, which means afterwards we should see that the total momentum is going to be equal. So what has to happen afterwards is that initially this brick on top was not moving, so it had no momentum, and now it's going to have some momentum. And these two that were moving are going to lose some momentum. All right, so think about now if we have 45 units of momentum at the end, and now we have essentially three objects, a cart and two bricks, and they're all the same mass. Essentially what's going to happen is that 45 units is going to be split up. So the brick by itself, that's the brick on top. Again, I'll just maybe circle this with a red. Okay, so this brick, again, is different than the other ones. What's going to happen is that brick is going to get a share now of that total of 45. So if all the three objects have the same mass, that means the brick is going to essentially get 15 units of momentum, and the other two objects, the cart and the brick, are going to get 30. So again, it's taking that 45 and kind of divvying it up. Essentially, I got these numbers because the objects are the same mass. But again, what happens is that the cart and brick that were, the loaded cart, I should say, lost 15 units of momentum, whereas the brick that was dropped on top gained 15 units of momentum, so the overall change was 0. So again, this bottom row here is showing us momentum being conserved because before and after is the same and the overall change is going to be 0. Last example here, kind of applying the conservation momentum, but here I have a 120 kilogram lineman moving at 2 meters per second, tackles an 80 kilogram fullback moving at 8 meters per second. And it says after the collision, they both move east at 2 meters per second. So now we're actually fitting numbers for momentum. So this table is going to look at the idea of momentum. So this is momentum before, momentum after, and then this is that change. Okay. Again, momentum is the mass times the speed. So if I want to know the momentum of, let's say, the lineman, okay, so I'll just put LM and FB for lineman and fullback. The lineman, what I'm going to do is I'm going to take its mass times the speed. So I'm going to do 120 kilograms times 2 meters per second. So that would give me 240. And then I have the 80 kilogram fullback moving at 8 meters per second. So 80 times 8 would give me 640. Now notice here that it says that the lineman was moving west and the fullback was moving east. And we talked about how momentum is a vector quantity because it pertains to direction. So I'm going to label the lineman's momentum as negative because of it moving in a negative direction. So think north, south, east, and west. West would be that negative direction. So when I look at the total momentum, what I'm going to do is I'm going to subtract these two values, and I would get an overall change, or total momentum, in the beginning of 400 units of momentum. Okay, so afterwards it says that combined, both players are going to move east at 2 meters per second. So the lineman is going to move at 2 meters per second, so it'd be 120 times 2. So again, that's going to give you, whoopsie daisy, wrong one, 240 units. And the 80 kilogram fullback is also going to be moving at 2 meters per second, so 80 times 2 would give you 160. Know that both these numbers, it says it's east, so they're both going to be positive values. So when I add those together, again, I'm going to get 400 units of momentum. So again, what this is showing is the momentum that I have before is going to equal the momentum I have afterwards. Now looking at the change, what happened to the lineman's overall momentum? So the lineman went from negative 240 to positive 240. So when I find the change again, that delta value, I'm going to take the final minus the initial. Okay? So the final was 240, the initial is negative 240. So careful here, this is going to be 240 minus negative 240, which essentially is going to happen is it's going to add together to give me a total of 480 units of momentum. Okay, so what ends up happening here is that the alignment is going to lose the original 240 plus gain an extra 240. The fullback is going to go from 160, it's going to start off at 640, go down to 160, so obviously he's going to lose. So if I were to subtract those two, what I'm going to get is negative 480. So notice I get the same number that I got before, it's just my signs are different because this object is going to gain the momentum, this object is going to lose the momentum. And therefore, the overall change in momentum is going to be 0. So again, this is just showing that idea of a law of conservation of momentum using these two-way tables. It's kind of a skill used in mathematics and looking at statistics, but it helps us to show how momentum is conserved.